Okay, so I wanted to thank you. It's nice to have a voice in SNOMAS. I know that the target and sources didn't have such visibility in the previous SNOMAS, so I want to thank you for that. So here, what we want to avoid is exactly this, is all this target failure, and they do fail. And this is many facilities. And so we have here a clad failure on ISIS TS2 that was pretty bad and led to contamination of water. Sink had also failure, and this was a cascade failure. This is something you never want to hear as a target engineer. Here we have the SNS, which is a mercury target, and you can see the erosion of cavitation through the vessel. Beryllium window embrittlement, Minos target containment water leak, and Nova Med 01 target fin fractures. And here we have a target failure, which is to the radiation-induced swelling. And so you can see it happens. And it's really not a nice day as a target engineer when you get the phone call and say that the target failed. You avoid the elevators. So this is something that is undesirable, and so this is what we want to avoid. There are right now already challenges with target failure. Major high power accelerator facility, SNS, JPark, Fermilab had to operate at limited beam power due to target concerns. So this is definitely right now a limitation for megawatt. It happens for megawatt accelerator. The fabrication is getting harder and harder. To avoid failure, you start to look at the fabrication. You make sure that the weld quality assessment is there. And so you have tighter quality control to reduce the risk of failure. You have a redesign of targets, and this leads to higher cost. And I can give an example for SNS. Our first target was 350K. Right now it's 2.5 million. They didn't change that much in geometry, but all the tighter quality control that we have on the target made the price goes up. So there is also a low availability on the market for some material. A good example is ESS. They literally built their target based on how they could find the tungsten. And so they are using this brick of tungsten because they realized they had a hard time to find a vendor that could really give the shape of the tungsten what they wanted. So more R&D is needed on the targets to allow a reliable and cost-effective operation at high power. So with higher intensity came bigger challenge for the target. We're going to get larger thermal shock. When the beam hits the target, it releases a lot of energy in the target, and the material wants to expand very quickly. This leads to pressure wave, and this is what I call the thermal shock. Higher radiation activity, which is going to reduce the lifetime of the target. Right now, it's not really an issue for many targets. But as we go higher and higher power, we will have to change the target just because of radiation damage. Operational safety. Now we are talking about remote handling for all the targets. Radiation protection. And the one issue to not neglect is storage and disposal. Right now in US, we use Nevada to trash all our targets. But I think it was 2 years ago, Nevada said, we don't want that anymore. And you are in trouble when suddenly the person doesn't want to take your waste and you don't really know what to do with your targets. We will deal with higher heat flux, and so you need to find a way on how to cool safely your target, and even more fabrication challenges. So right now, for instance, ESS is using a rotating target. The second target station at SNS is using that. You can see the design is getting more and more complex. The ESS target was built at Bilbao, Spain, and they had crazy constraint, mechanical constraint on it. I cannot believe they managed to build it. It's very beautiful target, but definitely it will come with a cost. Again, low availability on the market for some material, and developing new material is not that easy. It takes a long time before reaching a commercial grade. So it's not as if you find something better, is going to be available right away in the quantity you want. So we were pretty impressed, in fact, when we started this SNOMAS process. The target community responded pretty massively. We got 19 LOI just on targets. And so what we did is that we look at all the LOI and basically identifies the main R&D path. And so there was a lot on the material studies to extend the radiological material science. And so it including radiation damage in material, post-irradiation examination or PIE, and irradiation station. The second topic that came developed was modeling and how to improve modeling to capture more physics, to predict the target lifetime better, more code integration, leverage of AI to optimize the target design. The third topic was novel materials and novel concepts. Another one was the radar instrumentation. Many of the targets are not very well instrumented because there are not that many instruments that can resist radiation. But there is a dream at SNS to have a sensor that will tell us when the target is about to fail, which will make our life much easier. Remote handling and operation, and how it could be leverage maybe AI for operation, and some specialized physics targets. So overall, we're pretty happy. And so what we did with this LOI is basically we organized a workshop based on that. And so we had a workshop on target modeling and another one on irradiation station, one on radar instrumentation, and we had also another one in collaboration with Eric Prebis and AF5 on the targetry needs for neutrino. And almost all of them came up with a white paper. And so this is basically what will be in our report is this main white papers on these 4 different topics. So irradiation facilities are needed for radiation damage studied, for thermal shock studied, for fatigue study, for validating target concepts or prototype, for modeling validation too. We do a lot of simulation, and we have generally very few data for the validation, especially on the mechanical simulation. And so modeling validation for radiation damage, target design, and beam matter physics. So here is a small table, what can we do with these irradiation facilities? And the best we could is to have the high energy proton, because this is the same beam. But let's be honest, there is no 2 accelerators in the world that have the same beam. So it's very rare to find a facility that can generate a proton beam that is relevant for you. So even though the thermal shock is good, and unfortunately we get activation, the damage rate is low, we can get a large quantity of samples, and we get the gas production. Gas production is very important for us because it will affect the property of the material, like thermal conductivity. So it's something that we are generally looking after. But as I said, it's very rare you can find this one. And so generally you look at maybe lower energy proton, and so you get a little bit less gas production, and you have to basically content yourself to a lower quantity of samples. And so another way is to look at alternative beams, such as electron beam with a pretty good options, but you will get a relatively low damage rate and very low gas production. And so you may have to use another kind of beam irradiation to create that gas production. We have low and high energy AV ion. What's nice about the low one is that you get no activation, and so you can directly do the measurements on the samples. But you don't get any thermal shock. The damage rate is very high. And the quantity of irradiation material can be, however, very small. And the gas production, again, is none or low, meaning that you will probably need another beam irradiation. And the final one is a neutron, which can give a very large quantity of samples, which is sometimes what you want for material science. So we also need to expand our post-irradiation examination capabilities. And so here we were especially thinking about the high-power targetry lab at Fermilab. There is not that many places where you can get your hot samples and have a test on it. For SNS, we are using Westinghouse. We don't have any very good capabilities at RNL for high activated. We have a lab for low activated samples, but not very high. And we need to promote the PAE programs at other accelerators and other labs, like Lambda at RNL. We need to compile a database on experimental data on irradiated material. So what's very funny is that there is kind of a gap right now between what we do for the target for accelerators and the nuclear community. And so the nuclear community has a lot of data, but not on materials that are maybe very relevant for us. But for instance, they have a lot of data on stainless steel. And it would be nice if we could basically kind of work with that community to compile a better database and compare a little bit of knowledge here. Develop procedure to test and validate novel materials. As I mentioned, it takes a long time to validate a material. And we need to basically find a way to reduce this length cycle and basically being able to use new materials a little bit faster. And finally, it would be nice if we could develop a user facility program for irradiation stations similar to NSUF. So for instance, if I want to have a material being irradiated and want to go to Los Alamos, I have to pay Los Alamos. And it is a little bit silly because we are all working for the same agency here. Modeling needs. So one thing about Target is that there is a lot of interfaces between different people. It starts with a particle physicist that after work with mechanical engineers and designers. And so there is a lot of handshake in the simulation. And right now this handshake is not that easy because the codes are not really using a standard form. And so I think there is a lot of work that could be improved here. And this is something that was talked yesterday by Jean-Luc too, is that code interfaces is something that is often neglected and should be better done to allow a design exploration and optimization for Target. Better accuracy. So we could improve physics models, and to be honest, some of this model would be better just if we had better property for the material. And right now, you know, the way we do our simulation, we make strong assumption on the variables, and these variables we assume they're constant, whereas the truth is they are decreasing or increasing with the irradiation time. And so there is something that could be improved here. And so again, here is transient simulation, where basically time-dependent material properties. But for this kind of simulation, you really need to scale up and think about HPC. We need to develop numerical tool to predict radiation damage. We have some good white paper on this, and there are some tools available right now. It's really starting a little bit, but it would be very nice to have a code that could really explain us how the radiation is damaging the material. Right now, the only tool we have is from particle physics, is a DPA, but it's just a variable. It doesn't really explain very well what kind of radiation damage we get. And we need better verification and validation. And so for that, we need irradiation facilities for controlled experiments. So right now, we are reaching the limits of conventional material. That's why we're getting more and more target failures, because we are just at the edge. Before, we had some margin, and so it was not too complicated to design the target, but now we are just reaching the limit. And so there is really a need of novel targetry materials. And so this is a kind of novel materials that were given in a white paper, which is a high entropy alloys, electrospun nanomaterials, silicon-coated graphite or silicon-silicon composite, toughened fine-grain recrystallized tungsten, titanium alloys, and advanced graphitic materials. In fact, Frederick listed some of them during our Wednesday talk. We also need novel targetry concepts and technologies. So right now, the rotating target for neutron sources is kind of popular. We are flowing mercury, and we are thinking about circulating targets like granular tungsten. So we need to think a little bit outside the box on what the target can be. We need advanced cladding materials and technology. So, you know, most of the time we use water to cool our targets, but some material doesn't do well with contact with water, and so you need to clad. But cladding is not that easy. You still want a very good thermal contact. CERN has been doing great work on this topic. And I think we are a little bit lagging behind in the US. We need target geometry and composition optimization, high heat flux cooling, and advanced manufacturing. I mean, right now, 3D printing is making huge progress. And I think we should consider more and more, can we 3D print a target? Okay, one last thing is the radiation instrumentation. So better instrumentation allow better verification and validation, machine learning opportunities, digital twin, and target health monitoring. Most of the time, targets are poorly instrumented. It has a few temperature measurements. If you're lucky, you may get a target imaging system to see about where the beam is deposited. But this is not enough to validate any of your thermal mechanical simulation. So here at SNS, we started to put a strain sensor, and so you can see it's pretty busy. We put about 20 sensors. Recently, we collaborated with the University of Pittsburgh with Kevin Chen, Professor Kevin Chen, to make a Snoopy on the target, as I call it. It's a fiber that measures the strain along the length of the whole fiber. So instead of having one measurement per fiber, no, on this one, I think we were getting about 10 measurements on the fiber. And I think this kind of collaboration with university is great. Professor Kevin Chen was mainly working for an SUF, and I kind of drag him at SNS and say, hey, we'd love to try your fibers. And this is where I think, we can really benefit. It's more collaboration with university on this kind of very niche problem that we have. Another example of instrumentation here is showed as a JPark, where they are measuring the vibration of the target with the LDV system. And so they have a tiny mirror on the target and a path for the laser. So definitely not that easy to instrument your target. It definitely takes some thought and some work. And it's much easier if you think before than doing after the fact, like we have been doing here at SNS. Collaboration effort, and so this is key in my opinion for the target community. One good collaboration that has been working since 2010 is Radiet for material studies and modeling. It has about 80 participants and 14 facilities, and it's expanding with time. It generates new and useful materials data for application within the accelerator and fission fusion communities. Another collaboration that has been working pretty well, we are meeting every other year, is a high power targetry workshop. And it has all the major high energy laboratories from JPark, ISIS, Triumph, or SNS or Fermilab. And right now it started in 2003, and we have been meeting every other year, except with COVID. And we should leverage collaboration with other communities, like light sources, in fact, have similar challenge than us with their beamed up and collaborator. And so we should expand a little bit our view of what exactly problem we are seeing. There are many other applications that see similar problems, beam dumps, windows, and so collimator have very similar problem, and we should a little bit expand a little bit more than just looking at targets. Other communities that have similar challenge is a fusion. They need high cooling too, and so again, there is things that we can talk to them and enhance our simulation. In fact, we often find that they have similar challenges for instance, for their particle matter simulation. So our main message is that we want to a development and validation of alternative beams to simulate high energy proton irradiation. This will be a key, in our opinion, to develop a solid database for material science. Development or upgrade of post-irradiation examination PIE facilities that will allow to test novel materials or extend our current database. A development and validation of numerical tools to predict radiation damage. It's true, it's very tempting to improve other model, but we think that this is more a low grapefruit and could bring results very quick. Developing a radiation resistance sensor for better numerical validation of the structural and thermal simulation, and potentially to do machine learning or digital twin application. It would be great if we could predict much more accurately the span life of a target. When your target costs 2.5 million and you remove it and open it and realize it has no damage, you kind of cry a little bit. So in terms of actionable items, what we would like to see is basically strengthen the high power target community through the Radiate collaboration and high power targetry workshop. It would be nice to see some fundings for having more universities to participate to this kind of effort. Leverage the synergy with the other community facing similar challenges. So it's a little bit of work from the target community here. It will be great to see a development of a DOE sponsor user facility programs a little bit like NSUF, so that we could have access to irradiation facilities without having really to find the fundings for it. And I think that's about it.
Thank you. Nice talk. Very informative for a novice. So who funds Radiate? Where does the money come from?
I'm pretty sure it's by Yard, right?
I mean, I'm online. I can answer. So can you hear me?
Yes.
Okay. So Radiate doesn't have any funds. I mean, Radiate collaboration is really to connect the different experts in the different institution, but each institution will follow its own program on their side. And
Right, so
we try to work to have some common experiment, but everyone support their own program.
okay. So my other question was, how much GARD funding do you guys get?
So we have some GARD funding at Fermilab. So if I don't mistaken, it's few $100,000. So around 300 per year.
Oh, okay. It doesn't really get you a facility, does it?
No, it's really not a lot. So we try to do as much as we can. And that's why we are seeking always collaboration also to lower the cost of the R&D.
Okay. Then one last thing, just a comment sort of and a question. So years ago, I was at Oak Ridge reviewing something about SNS, and the target guy was talking about their target failures. Because of the complexity of their target geometry, they had to do a lot of welding, and the failures are mostly in the welds.
Yep.
And so I asked him, what about 3D printing? And you mentioned it. And at the time he said, well, they're too big. So what's the obstacle now? Has anything improved?
Mainly safety, folks. If you think about the 3D printing, it's a huge weld. And so the 3D folks are not, as long as right now, if you talk to 3D printing experts, they don't have a SME process to validate the material they're producing. And so because of that, we cannot make a simulation that's gonna say this target gonna survive the beam. And because of that, the safety folks are saying no. So it's very annoying because we have a huge facility at Oak Ridge. Well, it's at Knoxville, but just nearby the lab that do 3D manufacturing. And, they're tempted. But every time, when it's time to say, well, what's your process to certify your material? They don't have any. And that's where we are. And, we are kind of begging, just let's print one and just make a test. But we are not, a target facility. We are a neutron facility. They don't want to make tests on target. They want to produce neutrons. So it has been clear to us that, it will not happen.
A couple questions and comments here. This is Bob Zwaska, by the way. So yeah, I agree entirely that it would be nice to just test a 3D printed target and see, you know, what the different effects are with it. And I think putting them into practice, they have to figure out this material properties validation thing. I mean, that's entirely necessary. But, you know, it's still an active area of research. So, I mean, we could say something in terms of 3D printed materials based on our results. You know, I mean, I could imagine, you know, a lot of them are sintered and things like that. I could imagine the gas production operates very differently. They're all often voids inside that material. Other things is I absolutely agree about some form of DOE sponsored user facility. And I hope this is just a message that can be clearly put in the report and they can hear it, because they do already have this NSUF that you were mentioning, the Nuclear Sciences User Facility, which is really earmarked only for nuclear energy, not even nuclear science. And it's always been a frustration that, you know, the Department of Energy has these facilities and these capabilities, and we're locked out of them. So that's frustrating. The question, other question and comment I had was on the use of codes, improving radiation codes and the interfaces between them. You know, I'm both a user occasionally and a stakeholder with some of these simulation codes. And as they've become more capable and more complex, they sometimes become less useful, especially when it's in a design process. You know, when they're able to have geometries that are so complicated and are very time intensive to implement. Doesn't matter how fast your computers are. It takes forever to get the geometry right, and they have to be iterated. And then you might have one code for radiation damage, another code for particle fluences, and then it has to go into some kind of thermomechanical code to understand the effects. And then you might change the design a little bit and have to do the whole thing around. And it becomes really prohibitive to do any type of design studies. Now, understanding an experiment where it's more linear, you know, perhaps it works there, but it's gotten to be really problematic with designs. And as the codes become more complicated, people put more faith into them. So I think what we need is a little bit of ways to short circuit that process. You know, rules of thumb, scaling rules. You know, if you change, you know, the size of one of your internal baffles on your mercury target, right? You know, from, you know, 1/4 inch to 3/8 of an inch, you really don't want to have to start over. You'd like to be able to just be able to scale the energy deposition and get a feeling what will happen to the material without having to, you know, spend 3 or 4 months on simulations. And I'm starting to feel like we're really losing the capabilities to do these scalings and you know, paper and pencil calculations. And instead we're spending months and months of computer time, and it's gotten very difficult to design anything.
I agree. There is a sweet spot to find where, you know, you can, because the iteration through all the people and all the experts take forever. And when you want to do optimization, it doesn't work anymore. And so, but there are now more and more tools that are available to not make this iteration. So I've been looking, for instance, you know, when we do all our beam matter simulation, for me, they all look the same. When we change the thickness or we change a little bit the shape at the end, they look kind of similar. You can almost predict them by the eye. And when you say that, that means that you could have a machine learning algorithm here that could start predicting, you know, the simulation that take 2 weeks in 10 minutes. Right. And so we have been starting a little bit playing with that, such that can we, instead of playing the big guns, you know, big guns code that, you know, take 2 weeks to get the converse solution, use just something that is a little bit simple and gonna give you a 80% good idea of if you are going toward the right direction or not. So I think there are options for that. But at the end, you still always need to validate the target, and you always need to go back to the, you know, full-blown mode simulation to make sure that you are 100% right. But there are many tools right now, for instance, for thermomechanical simulation, they use GPU, and you can literally change your geometry and see the results and the impact on temperature and stress right away on your screen without waiting 2 or 3 hours for crunching the numbers. So there are like very cool tools coming up. And it will be nice to see better interface so that we can include these tools in the design that make it much more dynamic than you know, uploading your input files and waiting a week and coming back a week later.
Right, and even having to hand it off between different experts is very costly, right? You know, radiation modeler versus a modeling engineer, and you know.
But you know, you're completely right. Like I remember, like my physicist, and I was, well, how confident you're about this number on the back of the target? And he would say to me, 20%. I have, you know, plus or minus 20% error on these numbers. And these numbers mattered a lot for me.
I see. Okay.
And so, you know, when people were saying, well, why are you not using more accurate technique on your simulation? And I was, why? I have 20% error from my inputs from the physicist. I'm just, you know, you need to find the right balance. That's for sure.
Okay. Well, yeah. So I think that aside these computational tools, we also need, you know, the analytical tools of, you know, maybe some kind of handbook or something to get started. I mean, one example we have is this UDE2 that we were talking about, and we would like to be able to design a target for it, but we can't do the materials research which you would like to do until you really know what the target material is, and it's hard to even get started. You're just testing some concepts, because if you have to go to these computational tools all the time to get the results.
Mm-hmm. Okay, any other question? Okay.
This is about the DPA metric. So did you say that comes from high energy physics, the DPA?
Well, for me, I get it from the neutronics folks. So the beam matter, you know.
Okay, I didn't know it originated in our field. I mean, so what kind of metrics do you think might be more useful than DPA? Some people, you know, are very religious about DPA and don't think that anything else matters.
Well, you know, I think it's a good first thing, but at the end, I think it's gonna fall short to predict the impact of radiation damage. And so this is where I think, you know, you're gonna be more interested on knowing how much gas is being produced or stuff like that. And so I think the DPA is a good first thing, but at the end, I will not be surprised, you know, along the line, we're gonna realize that, yeah, it's not enough to really predict the radiation damage accurately.
Okay, yeah, I could see that, but yeah, it's a funny metric because it's actually challenging to calculate it by hand, you know, from first principles and cross sections. But it's much more useful than having to deal with, you know, a neutron flux, right? You know, like 10 to the 21 neutrons per square centimeter with a certain energy spectrum, and how do you compare one situation to the other? So it's definitely useful having something like a DPA or a number of things like that. Another problem with it is that it's very nucleus dependent, right? So, you know, if you take the same beam and put it, you know, into hydrogen or tungsten, you're going to get, I don't know, maybe 500 times as many DPAs in the tungsten as you will the hydrogen, even though it's the same radiation field. So I think there's definite improvement there. I kind of hoped that there were radiation damage experts outside of particle physics that would be consulting on numbers like that.
Yeah, I mean, you know, for it's kind of a niche, and this is where if you are collaborating with the university is very helpful, because as an accelerator, you cannot really justify to have a person with such deep knowledge, but the university can. And so this is where I think, you know, it really matters to have, you know, university help us on this kind of very niche problem. The same way with the cavitation issue we had, I had a collaboration with university, and they have like amazing tools to simulate, you know, cavitation that we will not have at SNS. Okay, well, I propose to just follow up with the sources. Okay, I'm going to need your help here because I'm not sure what is showing. Okay, it's already shared. Yeah. Okay, so the next talk is about sources, and this is definitely not my background. However, Yinsen couldn't make it today. She had already something, and she couldn't be here virtually or physically. And so I do want to cover over the work because the source community did a great job. They have two very good white paper that is very comprehensive. I think one of them has more than 50 pages. And they did work very hard for SNOMA. So I wanted to at least, give them some visibility and show you a little bit the results of this. So I'm going to go through the different kind of sources and what really need to be done. And I'm sorry, it's a lot of text. So for the electron sources cathode, it's first, it's the highly polarized electron sources are required as probes for high energy physics. And so developing a steady, robust, and reliable source for the heterostructure-based cathodes such as gallium arsenide, etc., in the near term is of utmost importance. The cathode lifetime study is strongly linked to the development in electron guns and drive laser technology. For unpolarized electron source with high quantum efficiency, small intrinsic emittance is another area for cathode development. Research towards future cathode technology calls for a collaborative theoretical and experimental effort between the fields of material science, condensed matter physics, and accelerator physics. Development of cathode testing facilities is critical in testing the performance of novel photocathode candidate materials in electron guns and under realistic operating conditions. For electron sources as gun, DC guns have better vacuum, which allows a better lifetime for polarized gallium arsenide cathode. Highest average current under continuous wave operation were demonstrated with the DC guns. RF guns can reach a higher accelerating gradient, which is essential for low beam emittance and high brightness. SCRF guns have comparable vacuum condition with DC guns, but can provide much higher accelerating gradient. DC guns are reaching for high operating voltage to mitigate space charge forces, maintaining high vacuum condition to preserve the gallium arsenide base for the cathode lifetime, and managing ion back bombardment are important area for future R&D. For NCRF gun, push it for high accelerating gradient in the direction of high RF frequency gigahertz guns. Copper structures operated in cryogenics temperature have the potential for both higher gradient and repetition rate. Higher average current is more manageable in low frequency RF guns. SCRF guns and normal conducting photocathode insertion into a SCRF gun is a challenging aspect in the SCRF gun technology. Collaboration with leading labs should be encouraged for the development of SCRF guns in USA, such as the LCLS2HE injector, SCRF gun injector project. For the injectors, the electron injectors delivers beam up to 100 MeV. The injectors can be either CW or pulsed. Achieving a high 6D phase space brightness and manipulating the phase space distribution of the electron beam to fit its application should be invested. This includes the photo injector drive laser shaping, round to flat beam transformation, emittance exchange between transverse and longitudinal phase space, pulse string generation, etc. Reducing dark current is one of the most important topics of CW electron injectors. Laser or plasma Wakefield-based electron source focus on the generation of unpolarized electrons have demonstrated impressive beam parameters, but their application as a driver for HEP collider are still far from becoming a reality. The critical challenge in advancing the state of electron cyclotron resonance of ion source or ECRIS lies in achieving higher magnetic field to support operation at higher heating frequency and to provide stronger plasma confinement. Development of a fourth generation ACRIS. The R&D work is to develop a magnet system that can produce a needed magnetic minimum B field configuration with either niobium titanium or niobium, not sure, 3SN conductor. This is the most urgent task that needs sufficient funding to move forward right now. If the Mars magnet geometry gets validated in ACRIS, an HTS or hybrid-based Mars magnet capable of generating magnetic fields for operating at 80 gigahertz will be the pathway to a future generation super-performing ACRIS. After the issue of higher field magnets has been overcome, higher frequency microwave generation with suitable power level in CW mode for ACRIS operation could be another important task, and that should be addressed. For the laser ion source, this is a simple ion source that can provide intense pulse beams. It has a high repetition rate operation. The laser pore density must be increased to obtain high charge states, but this results in cratering of the target, and the target supply cannot keep up during the high repetition rate operation. To solve this problem, tape targets can be prepared and run at high speed, or liquid targets can be prepared. Long pulse widths, the pulse widths depend on the velocity distribution of ions in the generated plasma. If the velocity at which the center of gravity of the plasma moves can be reduced, the time difference within the pulse of the plasma reaching the extraction field can be increased. To achieve this, a foil with a thickness of less than 1 micrometer could be used as a target. However, in this case, the plasma could not have enough initial velocity and will be expected to diffuse in all directions. To prevent this ionization in a high magnetic field and limiting the direction of diffusion may prevent the plasma density from decreasing. Generation of high charge state ions from heavy elements optimize the laser irradiation condition for the species and charge state. The laser pulse width survey will be a useful strategy to have optimum laser irradiation condition. Instability of the ion beam is often caused by the roughness of the target surface, and so to prevent this, the beam can be further stabilized by adjusting the lens position while precisely measuring the position of the target and focus lens. On the charge breeders, future RIB facilities are expected to significantly increase the production rate of rare isotope by several orders of magnitude. Such facility may necessitate the implementation of the two systems, ABIS and ACRIS breeders, for complementary in charge breeding RIB of different intensity ranges, ACRIS high intensity and ABIS low intensity. R&D in high current density electron guts for ABIS breeders is needed for efficient charge breeding for high intensity beams. This would enable two operating modes: a pulse injection at high repetition rate to remain within the charge capacity limit of the upstream cooler buncher, and a continuous injection with longer breeding time for a beam rate exceeding the buncher capacities. Such guns will also allow for the reach of lower AQ values with higher efficiency, with shorter breeding times, extending the energy limit of post-accelerated beams to isotopes having shorter half-lives. A long-term target goal of 4 amps and 5,500 amps per centimeter square is suggested. The pervasive background of ACRIS breeders can substantially contaminate RIB of low intensity. The development of new techniques and designs to reduce it should be considered a priority. ACRIS breeders generally operate with a single and fixed microwave heating frequency, leading to a fixed element dependent charge state distribution. This limits the energy range of the post-accelerated beams. Fine frequency tuning, two frequency heating, and the afterglow effect can allow for low charge states to be optimized to maximize the breeding efficiency of short-lived isotopes, extending with those isotopes the energy limit of post-accelerated beams from ACRIS breeders. R&D is ongoing and needed in this direction. Constant progress in numerical simulation tools and advances in computing power is enabling the development of increasingly detailed, safe, consistent numerical simulation codes for ACRIS and ABIS breeders. The development of complete ABIS and ACRIS breeders 3D numerical simulation code is highly necessary to improve their performance and should be set as a long-term goal. This appears accessible in the future with increasingly faster computer and the availability of computing centers. ion source and machine learning, the optimization of an ion source operation space, some tens of parameters, is difficult and time-consuming for a human. The application of machine learning to this task promises advancement in both source performance and the maintenance of stability. And the optimization of ion source via machine learning is still a young area of research. It should be expected that efforts directed to the application of machine learning to ion source operation will result in real successes in the not too distant future. And I think that's about it. So I cannot really take much question because this is not my background, but any comment, will be welcome so that I can give that to you now.
So I just comment, I mean, we talked about this, a year ago, the lack of interest in positron sources. Nobody came out of the woodwork to propose anything. And this is it's a big deal for all the E+ E- proposals. So I don't know, I'm just
Yeah, I guess maybe I can comment on that. We were approached a few times with positron sources, but more so from the target point of view, and only on it was more or less focused on design issues, so that there was very little in the terms of material R&D. So it became a design task, and I think this was just for the ILC, and so there's already a body of existing work that's been done, most recently in Germany, and I don't think this is such a high priority for them. They need positron sources, but there are so many other issues and costs. This is viewed as a relatively small cost item.
okay. So perhaps you're just waiting for something to happen.
Yeah,
so
I think
come in and
I think the to realize something like an ILC or something, is, well, you guys have estimates, but on the order of 15 years or something like that, and that's probably enough time to design a positron source.
So I know that Yin, reached to them and tried to get a workshop, but didn't get really momentum on it. I cannot see, do we?
Hi, this is Atul. So actually I see we discuss lots of things about machine learning applications, but we have to think about how to generate large samples. We need lots of samples for the training algorithms. So it's a kind of, we need to set up several configurations, different configurations, and then we need to generate large amount of samples. So it's a costly thing, I think, but we need to think about how to generate those samples with different configurations. So do we have any, is there any plans or anything like that? So
Yeah, I will not be able to answer the question.
As a comment, actually, a question about the last item, about this machine learning application to ion source. Actually, machine learning was applied to ion source by Los Alamos group in 90s. I think that story wasn't that much successful, I was called, because in the 90s it was being used, and then it disappeared for quite a long time. And as recent years, as this booming of AI ML, it starts come back. I really highly doubt about what they're claiming there.
Yeah, I mean, I agree with you. We heard about AI in the 80s and it's kind of coming back. I think that the main difference is the hardware, is that you can really do like a live AI that can easily respond to what you're measuring very quick. And so I think that that's where most people are going back to this machine learning and AI, despite having, tried a while back on it. Is that no, the hardware is good enough that you can really have a live system that's gonna optimize your source, in a live mode.
So hopefully they basically attribute this to this advanced or this new hardware thing. So now they can have do more like a real-time optimization. Or,
Yeah, I think that's what people are really hoping with machine learning.
okay, thank you.
Okay, well, I propose to have an early lunch. Okay.
All right, we're gonna end the meeting unless there are any questions on Zoom. All right, it doesn't look like there are any, so thank you.